Hello everyone, this is the fourth lecture of this week. Last class what we did is we demonstrated the torsion formulation through one example. We chose example of a shaft with elliptical cross section. We derived the expression for stress, expression for warping, and then when that ellipse becomes a circle, then the solution is consistent with the solution that we had in strength of material. And also we saw that the warping of the cross section when it becomes a circle is 0. Now, let us continue with the same thing. The purpose of today's lecture is two. First is we will see one more example of a different cross section, and then so far we have done stress based formulation. We will see what is the displacement formulation for torsion problem. So, let us start with another example. This example is the cross section is an equilateral triangle. As far as steps are concerned, it is exactly same that we already discussed in the last class. It is just we are demonstrating the same steps to different examples and then checking how this warping function is different for different problems, how the stresses are different for different problems, but the essence of the steps are all same. Okay. So, what we let us start with this example. So, first thing we have to consider the expression, we have to assume the expression of psi, and then expression of psi should be such that it vanishes at the boundary, and the expression that we chose in the case of elliptical cross section is the equation of the ellipse. The same thing we do here. Now, since it has three components, three parts, so these three lines have three different equations. So, what we can do is we can, for instance, what is the equation of this line? If we write the equation of this line, equation of this line is x is equal to x minus a is equal to 0. And then if we write the equation of this line it becomes x minus root 3 y, you can check it, plus 2a that is equal to 0, and then equation of this line will be it is x plus root 3 y plus 2a that is equal to 0. So, this is the equation, right. Now, then we can take psi as psi is equal to some constant, the same constant, then this is equal to this x minus root 3 y plus 2a, and then x plus root 3 y plus 2a, and then finally x minus a. And I look at this, if you express the psi, if you substitute the values of x and y at the boundary, the psi becomes 0. So, this is our assumption of psi. Now, once we have that psi, you have to determine the constant k. Now, what is the equation? The equation was del 2 psi, the Poisson's equation, that was is equal to minus 2 mu alpha. Mu is the shear modulus and alpha is the angle of twist per unit length. If we do that exercise and del 2 operator is, we know that del 2 del x 2 plus del 2 del y 2, right. Now, if we substitute psi in this expression and then calculate the value of k, the k will be, you can do this exercise, I am just writing the final expression, k will be minus mu alpha by 6a. So, this is the expression for k, constant k. So, we have the expression, now we have the expression of psi as a function of x and y and other material parameters. Now, once we have that, then you recall we also know that since psi vanishes at the boundary, it satisfies all these boundary conditions, all the traction boundary condition at the surfaces. Now, the end boundary condition will be end boundary condition is where at the end where torsion is being applied, and that relation between the torsion T and the function psi, the stress function psi, we know that relation is T is equal to 2 into integration over the cross section or psi dx dy. Now, psi, the expression of psi is known, with k is this, and then you can substitute this and we can integrate the entire thing over this triangle. And if we do that exercise, that expression will be T is equal to 27, I have the final solution with me, 5 root 3 then mu alpha a to the power 4. A is the this is how the A is defined. 3a is the height of this equilateral triangle. Now, this is essentially becomes 3 by 5, you can write it 3 by 5 mu alpha then j. J is the where this is equal to torsion T. So, this is the equation, okay, where j is equal to this j is equal to polar moment of inertia, that is for rectangular cross section here this is equal to 3 root 3 a to the power 4, that is polar moment of inertia, okay, or second moment of inertia. So, this j is equal to I x x plus I j is equal to I x x plus I y y. Okay. So, this is the relation between torsion and the angle of twist. Okay. Now, once we have that, then let us find out what is the distribution of stresses. Now, recall only non-zero stresses are sigma x z and sigma y z, all other stresses are 0, because we are only considering the torsion. Now, the non-zero stress components are related to stress function. That relation is, if you recall, sigma x z that is equal to del psi del y, and then sigma y z is equal to minus del psi del x. Okay. Now, if we substitute this relation, if we substitute psi from here and write this expression, and then final expression of this will be, so this will be mu alpha by a, you can please check x minus a into y, and this expression will be mu alpha by 2a, now x square plus 2ax minus y square. Okay. Now, look at let us see whether it is by intuition, it is consistent with our intuition or not. See what is sigma x z on this plane. If you take on this axis, x is equal to a, what would be the, this is x axis, and this is y axis. So, on this plane what stress we have on this plane, the stresses we have is only sigma y z, right. And what is the direction of sigma x z? Direction of sigma x z is in this direction, means on this surface, if you try to visualize, it is a 3D object, it is on this surface, but in the along the longitudinal direction, that is the direction of sigma x z, and that stress will be 0. Only the stress we have is in this direction because of the torsion, and which is consistent with this formulation. If you substitute x is equal to a here, then we see this is equal to 0. Similarly, if you take the component of the corresponding stresses on this and on this, and then check, those stresses will be also be 0. Okay. Now, this is the expression of stress. Now, once we have the expression of component of the stresses, we have to find out what is the maximum stress, what is the expression for tau max. Now, recall in the case of elliptical section, tau max, once we have the expression of tau, we can differentiate it with the coordinate axis and find out for which value of x and y the stress will be maximum. Now, one thing we observed, if you recall the example that we solved in the previous class, the stresses are maximum at the surface, and which is by intuition also we can say, based on the strength of material, you already had the solution of circular shape, and where the stresses were maximum, it is maximum at the periphery, at the outermost circle, right. So, that is on the surface, it is the maximum. Okay. So, if we have a circular section, so your stress is this, at this point this is the maximum stress. So, here also it will be same, on this surface only, on this plane the stress will be maximum. Now, look at, since it is symmetric with respect to the longitudinal axis, so all these surfaces your stress will be same, the torsion stress will be same. If it is same, then naturally we can say, if we substitute because finding stress on this surface will be easier, we can just substitute x is equal to a. So, finding stress on this surface, shear stress due to torsion on this surface is enough, because on other surfaces also the corresponding stresses will be same because of symmetry. And if you do that exercise, then stress will be, I will just write the final component of the stress. The stress will be tau max. Tau max is equal to, which is tau yz you get at x is equal to a and y is equal to 0, and this will be 3 by 2 mu into alpha into a. And if you write in terms of torsion, tau max will be, if you substitute alpha in the previous expression, we know the relation between alpha, and t, and if you substitute this relation into this, the final expression we get is 5 root 3 into torsion divided by 18a cube. Okay. This is the final expression for shear stress. So, this is how the shear stress and torsion is, the torque is related to each other, and the final is the, we have to find out what is the expression for W, and W expression, you recall how to find out the expression of W. The equation that we use is the strain, the sigma xz. If you recall, sigma xz was mu into del W del x minus this equation we already derived in previous classes, and sigma yz is equal to mu into del W del y plus alpha x. Now, sigma xz, expression for sigma xz is this and expression for sigma yz is this. Now, if you substitute expression for sigma xz here and then integrate it, get W, and in that integration we will have some function of y, because that integration will be with respect to x, and that function y, unknown function y, can be obtained by the second equation, this equation. And if you do that exercise, this exercise, as I said yesterday in previous class also, this exercise we have done many times in many examples in this course. Now, if you do that, the final expression of W will be alpha by 6a y into 3 x square minus y square. This is the final expression for this. Okay. So, this is the warping W. Now, so you look at the steps, as far as steps are concerned, it is exactly same. The same steps we followed in the case of elliptical section, and if it is other section also, if as long as you are using this formulation, the stress function formula based on stress function, your steps will be exactly the same. Now, once we have W, let us see how, if we plot the contour of W on this area and how it looks like. It will be something like this. This is the displacement W on this. Similarly, you can plot the contour of tau x, contour of tau xz, tau yz. Now, so this is the displacement contour for rectangular, for triangular section. Now, similar approach you can follow for other section as well. For instance, if your sections are, your section could be square, it could be rectangle with different aspect ratios. If you have those kind of section, your section could be something like this as well. For instance, if your section could be something like, say, something like this. So, if your section is something like this, procedure exactly same, you follow, you know the equation of all these surfaces, you assume, we have to assume size such that when it is substituted on this boundary, that value becomes 0. Now, and then rest of the process is exactly the same. Now, let us see when your circle, these are the 3 different cases. The last extreme one is the square, and the first one is the rectangular section with aspect ratio this with a by b 0.5, when a is the smaller dimension and b is the larger dimension. Here it is close to 1, it is 1, and you can see how this distribution of the warping W, they take different forms if you have different cross section. Now, you can have a cross section like this as well. Suppose you can have a cross section like this, like a channel section, and this is subjected to torsion. And same way you can apply to get the distribution of this warping or the W, or to get the distribution of stresses on the area. So, what we have done so far is we have derived the formulation for torsion, and that formulation we derive is based on stresses. So, essentially these are the stress formulation, and then we also demonstrated that formulation through some examples, and other examples, other problems we can follow the similar approach. Now, let us now formulate for the completeness of our discussion. Let us see if we have to derive equation in terms of displacement the same way that we did in case of in the previous classes when we discussed plane strain problem. We discussed formulation based on stresses and based on displacement both. The displacement based formulation essentially was a Navier's equation. So, let us derive the similar equivalent equation for torsion. Now, so next is our second part of today's lecture is, okay, before that you see all the examples that we have solved so far, or not solved, but gave some example or the final expression. All these cases your domain, the cross section is simply connected domain, but you may have a domain cross section which is not simply connected, multiply connected. As I was discussing in the last class, suppose you have a pipe and that pipe is subjected to torsion, then what happens to the distribution of stresses, what happens to the warping, whether at all warping takes place or not, if takes place, and how to determine those, how to compute those values. So, that is an important problem. So, next class we will address this problem, how to, if your cross section is something like this, then how to deal with this cross section. But today let us derive the equation for displacement, okay, displacement based formulation. Okay. So, displacement based formulation, if we recall our once again means everything we have to write in terms of displacements. You recall when we actually for plane strain problem, when we derive Navier's equation, we use the equilibrium equation, and in the equilibrium equation we substitute a stress strain relation, and then strain displacement relation, and the final expression we get in terms of displacement. We did not use explicitly compatibility equation because that was not necessary, because you are writing equation directly in terms of displacements. Okay. So, it is the same for this as well. We will be using only equilibrium equation and the stress strain relation and strain displacement relation, right. Now, if you recall, these are the relations that we have. This is equilibrium equation, this is the equilibrium equation, and this is anyway, this is, we started with this assumption that all other stress components are 0 except sigma yz and sigma xz, and sigma yz and sigma xz is related to displacement as this. Now, this relation essentially stress strain and strain displacement relation both are included. Okay. So, now next what we have to do is we have to substitute these two expression into equilibrium equation, and if we do that we get an expression in terms of only displacement, and if we do that then your expression becomes this will, okay. So, if you do that then this becomes your final expression becomes del 2, you can check del 2 w del x2 plus del 2 w del y2, that is equal to 0. Okay. So, this is Laplace equation, del 2 w is equal to 0. So, if you write torsion the same thing in terms of displacement, the governing equation become Laplace equation, but recall when you wrote, when we had written this expression in terms of stresses, that equation became the final expression was in terms of stress function, the final expression was Poisson's equation. Okay. So, once we have this, then let us, if you recall, okay, then what we have is, so, this is the surface of this, this is the surface, this is, okay, let us use different color, this is the surface and this is R, right, and this is also okay. So, on this surface your tractions are 0 anyway, all these tractions, the T n, it is anyway 0. So, all these surfaces are stress free surfaces and the traction boundary condition needs to be applied here, and the traction boundary condition becomes, if you recall, the same. This is the way we derive, we have the traction, and on this surface all these traction boundary, all these tractions are 0, but since all these components vanishes, all component vanishes, because either nz is equal to 0 or sigma zz is equal to 0, only non-zero components you have is this. So, your traction essentially becomes this, right. Now, if you recall what was the expression for nx and if this is minus dx and this is dy and this is your n, this is your n, and this horizontal component is nx and ny, its the components in x and y direction is nx and ny, then the nx was dy by ds and ny was minus dx by ds. Now, this is S and its normal is n. So, if you write this expression in terms of its normal, then this becomes dy by dn and this becomes dx by dn. Okay. So, n is the outward normal this. Now, so if I substitute this expression here, and we also know that sigma z and sigma, in some of these in some places we already wrote it, that expression of sigma z. Okay. So, expression of zx, just now we had the expression of zx is equal to del w del x minus alpha y, that is, and then there is a mu here, and then sigma z y or y z mu del w del y plus alpha x. Now, if we substitute this and this into this equation, the final equation what we get is this. We get an equation like this. Okay. Now, so what we have, no, not that, before that let us write, let us see that. So, you get an expression like this, and then finally, what you do is you substitute this. If we substitute this dw dn, this if we take the derivative with respect to s outside, and then this we can be this part, the right hand side part can be written as, this right hand side part can be written as dw dn, and if we take from left hand side dw dn, right hand side if I take dds outside, then we have an equation like this. Okay. So, this is important. Now, then finally, we have to apply the boundary condition. The boundary condition is, these are the boundary condition, if you recall, these are the traction boundary condition. Now, these traction boundary conditions, all these boundary condition we can show that these on the surface, these homogeneous boundary conditions are satisfied. At the end, this has to be related with the applied torque. So, if this is the applied torque, this is the torque applied T. So, this should be equal to T. Now, if I substitute x, if I substitute expression of T y and T n, the expression just now we have, and in this, then the expression, final expression we have is this. So, since we have done this exercise for stress formulation, I am not doing it explicitly here. You can just, it is substitution of the expression and get the final form. This is the expression of T that you can get. Now, in that expression, if that expression again can be rewritten as this, but before rewritten as this, if we say that j is equal to this, from this expression, from the entire expression, this expression, if we define j as this and substitute j here, the final expression we get is T is equal to alpha into j. J is called torsional rigidity. J is called torsional rigidity. Okay, you see why it is called rigidity. Essentially, what you see, alpha is equal to you have T by J, right. What is alpha? Alpha is the twist, angle of twist per unit length. Now, if you take and this, if you apply torque, if you apply more torque, the angle of twist increases, but for a given torque, how alpha is related to J? Alpha is J is more, then alpha is less, means if the body is more rigid, then your angle of twist will be less, which is very obvious, and if the body is less rigid, flexible, your angle of twist is more. That is why J is called rigidity, and since it is related to the angle of twist, related to torsion, this gives you, this is called torsional rigidity. Okay. So, this is the final form of these are the formulation this is the formulation for the same problem, but written in terms of displacement. Now, let us we'll stop here today. What we do next class is, as I just said, this displacement based formulation is discussed just for the completeness, so that you know there is a formulation you can do, you can formulate this in terms of displacement as well, like we have done it in previous cases. So, this is the formulation for that. Now, we won't be doing any, you won't be demonstrating this formulation through any example. Now, next class is, as I just now said, we'll see how to address multiply if for a problem where your cross section is not simply connected, whether we can use the same set of equations or we have to modify the equations. If at all we have to modify the equation, how the modification has to be done. That is the subject of next class, which will be the last class of this week. Okay, stop here today. See you in the next class. Thank you.